Okay, folks, so I'm just going to run you through this really quickly here. So I'm on our Studio Cloud, so this should look fairly similar to you folks running our studio. So basically, I'm working off of this tutorial. I'm not going to do everything, and I actually don't recommend that you folks do everything either. Um, so I'll just kind of give you the cliff notes as to what you need to do here. So make sure you download the appropriate data. Um, I'll also attach the data you need if you'd like me to do that. So I'll send that along. But here's where you can download the data. And I went ahead. This is just a personal preference. I didn't mess around with making these directories. Instead, I'm just putting everything in my working directory, so everything's in one single directory. So don't be confused by that. I'm not actually using these, and I'm also not worrying about sharing code between machines because I'm on the cloud. Um, I don't think you need to worry about that either for this time around. And so basically, this is this is sort of talking about libraries and packages. So in the code that I'll send you, I have all the packages, so you'll need to uncomment these in order to install them one time. And then once you've installed them once, you can comment them out because you don't need to install them again. But you do need to always, then each of these, you need to say that you need to keep the library active. So that's just telling R that you're going to be using those packages during this session. And so I have all of those libraries listed. So those you will need to highlight. Okay, so that's sort of the first step here. So I've already installed the packages. I'm not going to worry about that. So I'm going to run the library. Okay, so we've got the libraries all in. And then there's this setting the coordinate reference system. And so in this tutorial, we're in South Africa. And so we're setting everything to UTM zone 34 south, WGS 84. And so that's basically what this definition is. So if you need to look at if you need to look at how if you need to look at how this is written out, you can look up pretty much any projection. So this is actually also identical to EPSG 32734. So you could use that as well. I'm just going to go with this nomenclature here. So that's going to be this value that's called standardized coordinate reference system. So that we anything that we map, we're going to want to make sure it's projected to this coordinate reference system. Okay, so we're going to start with the point data. And so we're going to bring in those seeders, which is a KML, so that's locations of trees. So here you can see in my code, I went ahead and set the coordinate reference system. And then here is where I brought in the seeders. So notice that I took away all of the working directory stuff because I've just got everything just sitting in my current working directory. Again, it's a little messy, but I was okay with it just for expediency's sake. And then here's where we check the projection, and then we're going to transform that projection into the one that we want to set everything to. Okay. So now we're also going to bring in the DEM, and notice that when we projected it, the layer that has the cedar trees in it, we're calling it PTS points. And so that's basically just transforming the raw points data with this new projection. Okay. And We're also going to bring the DEM in. Again, I'm not worrying about the um, working directories at all. All I'm doing is bringing the DEM in, and then I'm projecting it. This might take a little bit of time because you're talking about more data. So you want to get it projected to the proper coordinate reference system. Then we're gonna crop it because it is a big chunk of data. We don't want to be processing more of it than we need to. So we're going to define this E variable, which is going to define the aerial extent. So basically we're saying, okay, figure out how far out all those cedar tree points go, then add 900 onto it. And so that's just giving us a little bit of buffer to have a little bit of larger extent. And so so now we're renaming DEM is our cropped DEM, cropped to E. So we're replacing this DEM, which was the entire one. We're cropping it using E, and that's going to become our new DEM. Okay, so you can plot that. Okay, so we can go ahead and run. We can run that. So set coordinate reference system, bring in the DEM, plot the DEM. Okay, so we're going to run that. And let's go ahead. Okay, so here's our new plot. So there's our DEM. Everything's looking fine. And then we're going to add the points on, which are our cedar trees. Okay, so everything's looking good so far. Okay, so now using our DEM values, we can generate a lot of different variables. So these are all variables that we can use later. They're basically telling us about slope, which direction the slope is headed, how rough things are, and it might tell us, what are areas where cedars might be protected from fires versus not protected by fires. So we're just going to go ahead and calculate all those values. And then this is making sure everything's named appropriately. So this is making one single data frame called topo, which contains the DEM, the original DEM, the slope that we generated, the east-west that we slope rated, north-south that we generated, TPI, TRI, roughness, and flow direction. So all of that is going to be built into one data frame now. So we can run that. So basically it's showing, this plot is showing you all the different things that you generated. And then dense is calculating the density of cedar trees per per cell in the raster. So we want to rasterize the point data according to the DEM raster, and we just want to use count. So we just want to know the number of trees per pixel. And here we're saying we don't want to color the pixel red unless it has a density of at least of greater than 10 trees per pixel. So we should end up with a plot of the highest density pixels for cedar trees. So there indeed we do. So now we're going to bring in our other data sets. We're going to bring in our shapefile, our vegemap shapefile, which you can see here. And again, I'm using my working directory, so I don't need to use any kind of signifiers. So bringing in my vegetation map and making sure that it's in the proper coordinate reference system. And we can go ahead and plot that. So this is just a bunch of plotting variables. So this will take a minute because it's a large data set. Yeah, so you may have to be... Okay, so it's bringing it in. So now it's transforming, because that takes a little bit of time. So that's what we're waiting on here. We're waiting for it to get the proper coordinate reference system fixed for VegMap. And then what we're going to end up doing is I should mention, okay, so we're all the way down. We've gotten a good amount down here already. So we're already down here. We've already done that. We're bringing in the polygons. Let's see here. Then we should be making this plot. Let's see if it's done yet. Yep, it's done. So we've now made a plot with the different vegetation information. So these polygons are telling us which type of vegetation covers which areas. Okay, so we're good there. Okay. So now we want to be able to extract the type of vegetation that each tree is located at. So that's basically, doing this. So we want to know, okay, what type of vegetation is each tree located at? Okay. I haven't had success using drop levels, so we just won't worry about it. Okay. So when we look at the type of vegetation that the trees are sitting on, so you can see, if you end up making a summary, most of the trees are on the Cedarburg sandstone, right? We've just got a little bit of the trees located elsewhere, but mainly on the Cedarburg sandstone fynbos. Okay, so we've learned a little bit more about how our trees are distributed. Okay, so now we're going to bring in the fire data. So the fire data has to be brought in and transformed, and we want only the fires that are on the Cedarburg, because we're going to focus on that, because that seems to be where almost all of our cedars are. Okay, so we're going to bring in our fire data. We're going to project the fire data, and then we're going to only want the fires that are located on the Cedarburg. And then we want each fire to have a unique identifier. So all this is doing is labeling it 1 through whatever it was, 1 through 4,243, because that's how many fires. Okay, so it's just coming up with a labeled, so that each fire has a unique label. and then you're rasterizing the fire. So you're taking these shape files and you're creating rasters, and so that gives you sort of a fire intensity count for each raster. Sorry, for each pixel. So we want to know where are the most intense fires. We'll get a fire intensity count for each pixel out of that. Okay. So we can go ahead and run that and plot it. So that's calculating the fire count. Okay, so now again we've plotted our trees. And don't be confused, the fire intensity is kind of flipped. So green means higher fire intensity, brown means lower fire intensity. So here you can see fire intensity and cedars mapped on top of each other. Okay, so the next step is we want to actually create some animations, and I'm not going to do this. Oh wait, sorry. First, what are we doing here? Oh yeah, this is looking at. So I'm not going to actually run through this, but all this is because I did it, and I just don't need you folks to sit here and watch as my as the computer runs. So all this is taking that information, and because remember we have fire data for like what is it, 50 years, 60 years, 70 years, and so all this is doing is breaking it out by year, and we're going to use that to create these animations. So these animations take a super long time to load, so I'm just going to show you what the output is. So this is eventually what we ended up with, that you can see as the year counts up, it just keeps all the fires there, so you can start to see where some of the fires start piling up again. This is sort of reverse. High fire is green, low fire is red, but you can start to see where the fires pile up. Okay, so that took a long time to run to get those um, animations running. Okay, so here's just some other cool things you can do. So there's another DEM with a great color scheme, and it gives you, these are UTM locations, which is why it looks really weird. These aren't Latin Longe. These are UTM locations, which are pretty meaningless for a map. But anyway, you can do contour map, right? So this won't look too organized here, but you can also change the size. So anyway, this is a standard contour map. Then you can even make a three-dimensional map. That'll take a little bit to run here. And you can always export these. So again, there's your three-dimensional map showing the topography. Okay, so now, and again, you should be following along because this explains in great detail what we're doing, and there's a lot of checking steps that I'm not doing. So like, looking at the header data for the fire layers and seeing what kind of data you have. So I expect you folks to sort of continue to follow along. And then my code is just the very basics. So, and oh no, I didn't. You don't need to worry about checking it for speed, because we're not really going to concern ourselves with showing how parallel processing is faster. I don't think we're at that level yet. Okay, so we've done the animations. We've looked at some of this stuff. We're not going to worry about the Google Earth stuff. So now let's actually, try to understand a little bit more from our cedars. So, um, So we're adding fire count. Remember, we generated that big topo data frame, which had all the that had all of the information for slope and roughness and all that good stuff. So we're adding this fire count into that data frame, and then we're extracting the points data. So again, this is just we're making a little data set called points topo, just so we can take a look at the cedar data again. Okay, and so and again, this is adding density, so the density of trees. Again, we built this before, so adding this to the topo data frame. So that's just the number of trees per pixel. Okay, so now we're plotting density versus fire. So this is us trying to figure out, okay, what is really driving cedar tree distribution, right? Is it fire? And so you can plot density versus fire, right? So we've done this here. This is basically all that we did. Okay, so is it fire? And your plots are going to look a little different than their plots because we have updated data. Okay, so does fire alone? Or you could say, is it the roughness index? Does that explain it? Or the DEM, so just elevation by itself, does that explain it? The density of, we're trying to figure out what explains the density of these trees. Um, does the direction that it faces, does that explain it? So read up on these current theories, and so this is the last thing you're going to do, and we're not going all the way through, right? Is you're going to run this biomodel, and you're not including the 10th element because the 10th element is that density element. And so it's pretty ridiculous if you're using density to try to predict, tree density, tree distribution, because then, of course, there's going to be pretty much a one-to-one relationship there. So we're just kicking that out. Again, we're using that topo. So all this is saying is we're using this bioclimb model, and we're using all those elements that were in topo. So if you remember, okay, so if you remember, so the DM, slope, east-west, TPI, roughness, fire, density. Yeah, so all these things, except density, right? We're trying to see if you put all those in this model, what kind of predictions do you get for tree distribution? And then you're also going to plot, so then that's going to spit out a prediction, right? So this P is the prediction given those variables, right? You're going to run this model, and then it's going to give you its proposed distribution, which is contained in this element P. And then you're going to plot on top of that the tree locations. And so this is your model saying this is where we think, based on those values that you gave us, this is where we think the trees should be. Higher chance of being in the green, lower chance in the brown. And then we can actually put the trees over that. Now we could go further and evaluate the model, see how good of a fit it is. We won't do that. We'll stop right here. But so you should be able to get all the way through all that stuff. And again, I wouldn't expect you to write this code from scratch, but I would expect you to understand it and work through it. And again, Please do read all the details on this tutorial, because again, I gave you the stripped down code, but there's a lot of good information that'll help you understand how R can be used as a GIS. Okay.